Welcome, people of the Prague pre-seminar. The speaker of this week is Julius Benner, and he's going to give us an introduction to Hochschild theory. Please.
Okay, thanks for the introduction and thanks for the opportunity to talk here. So let me start with some conventions. K will be a field, um, characteristic 0. Probably suffices if the characteristic is not true, but let's make things as simple as possible. And the first section of the talk will be the Hochschild complex or the Hochschild space, not a complex yet. Of a K-vector space. So we fix we K-vector space, and we can make the following definition. So the Hochschild space I don't know how common this terminology is, but it's just to give it some name. Of V is C bullet of V, which is the direct sum n greater than or equal to -1 C n of V, where this Cn of V will be this space of homomorphisms from V tensor n plus 1 to V. So this is a graded vector space. Maybe to recall some terminology about graded vector spaces, we call an element f in Cn of V homogeneous of degree n. And we write it's like absolute value of f, which is defined as n. It's the degree of f. Okay, and how can we picture elements of Cn of V? We can think of them as some device that takes n plus 1 inputs. So because the domain is V to the n plus 1 and gives you one output. So I would draw an element of Cn of V as a box with one output and then n plus 1 inputs. Okay.
Why the shift? Why n plus 1?
You will see this in the next definition. Yeah. But it makes some things more convenient. But yeah, this Hochschild space, you could also say it's the suspended Hochschild space. But yeah, you are right. It does add a shift. Yeah. So next definition, the composition product. on the bullet of V. What's denoted by star is a binary operation. Is given by so if I take two homogeneous elements F and G, let's say F is homogeneous of degree n, so I have n plus 1 inputs, and G is homogeneous of degree n, so it has n plus 1 inputs. Then what can I do? Let's do it here. So the idea is I want to combine F and G, and so what I could do is plug the output of G into one of these inputs of F, but there's no preferred way to do this. So I just take the sum over all these possible ways. Right. So I have F. It was one input and then it's an ith input. Oops. I plug in G. And then in total, this gives me n plus n minus plus 1 inputs. And so this, because so I don't sum all these possible ways to plug them together directly, but also with a sign, which I don't want to get into. So this element lives in now Cm plus n. So this is why people are considering this space with this shift, because then this is a graded operation. Otherwise, you would get m plus n minus 1 if you don't apply the shift. So maybe I'll just see more concretely what this composition product does. Let's say I have an element m in C1 of V. So what is C1 of V? This is the maps, k-linear maps from V tensor 2 to V. So M looks like this, 2 inputs, 1 output. And if I look at the composition product of M with itself, in the picture, this amounts to this minus, so first I plug in M here, and then I plug it into the second entry. And this here we can already make an observation that tells us that this composition product is very useful, because composition product of M with itself is 0, precisely if M is an associative product on V. Hmm. Okay, what next? So maybe you will think the composition product itself is an associative product on the Hochschild space, but this is not the case. However, it has a different nice property, namely for all F, G, and H in C bullet of V. If I consider the composition product of all three of these maps, and I first bracket it like this, and then subtract from it the bracketing like this. This does not value to 0. Instead, it is the same associator, so a difference of these bracketings, but with G and H swapped. Yeah, sorry. And this doesn't hold on the nose, but again, up to a sign. And the sign is precise like this, such that the structure is a very specific one, namely a graded pre-Lie algebra. So oh, the Lie algebra. And as a corollary of this observation, we can define the following. Another map from binary operation on this graded vector space. And now this is given on homogeneous elements f of g by f bracket g is f composition product g minus, and the first instinct would be to write g star f, but because we are in a graded setting, the flip of two elements comes with a sign, and the sign in this case is minus 1 to the degree of f times degree of g. Okay, and we have this map, and the statement is, or this turns C bullet of V into a graded Lie algebra. So that is we have the bracket of f and g is equal to minus 1, I have to look, degree f times degree g times the bracket of g and f. So a graded symmetry and then ungraded antisymmetry. And then also we have a graded Leibniz rule. So f gh is equal to, Leibniz rule or graded Jacobi identity rather. But the way I write it here, it's more Leibniz rule. So this is equal to f bracket of fg and then with h plus minus 1 times degree f degree g f and then the bracket of Oh, no, wrong. So it's G and then the bracket of F and H.
Is the first one really like minus FG or minus of all of this? Because like
Okay, yeah, thank you. It's minus and then minus one to the degree F.
have like a usual algebra in degree 0. So if I simply think of not graded, this would give me a usual.
Yeah, that's what you would like to have the algebra in degree 0. Thank you. Okay, what do we see already? If we start just with vector space, we get something which has quite a lot of structure already. And now in the second part of my talk, I explain what happens if we replace V by an algebra. And this will be now the Hochschild complex of a K algebra. So if it's a K algebra, by which I mean associative, probably also unital, but we actually don't need this. And then, yeah, we have seen that we have an associative product on our vector space, then the composition product of this product with itself is 0. And this is very nice. Because then we can look at the following map. Which I call D, and which sends an element F to the multiplication of a thing. So here, MA is from A tensor. No, I don't have to change of V, but of A. A. Yeah, so this multiplication map lives in the degree 1 of this gray vector space. And so I can get a map if I apply the bracket with MA. And the statement here is that this turns CRA into a chain complex, co-chain complex. What I'm doing with time? Yeah, it's fine. Okay, and let's prove it because the proof is very easy and instructive. So the first observation is D of C n of A maps into Cn plus 1 of A. Because if I do the composition product of an element of degree 1 with an element of arbitrary degree, this raises the degree. And then we need to show that doing deep twice is 0. So that F being homogeneous element of degree n. And then what is the D of F? Yeah, that's just doing the bracket with NA twice. And now we know that this is a graded Lie algebra. So this amounts to MA F plus minus 1 to the degree of F MA MAF. Okay, now this term here is just composition product of MA with MA, and then minus 1 to the degree of MA, MA star MA. Okay, it doesn't matter. The sign doesn't matter, but the thing is, these guys are 0. So this gets 0. And then I just have that MA MAF is the same as minus MA MAF. And because wait, no, I put here the degree of MA, and this is 1, so here I get minus 1, and I get this. So in total I get dd of f is 0. Was this okay? Okay. Maybe as a corollary, if you consider all the structures I've mentioned so far, so the bullet of A, the Lie bracket, and the differential is a DG Lie algebra, or differential graded Lie algebra. So this means that C bullet A in the Lie bracket is a graded Lie algebra. And then all F and G in CA homogeneous, we have D of G is df bracket G plus minus 1 to the degree of F bracket dg. Okay, now I can make the nice definition. What happens, this is now a coaching complex, and I can look at this cohomology. This is called the Hochschild cohomology. So oops. Homology of A, or let's say the nth is HH n of A, comma A. And now I had a degree shift in defining the Hochschild space, and I need to reverse this. So the nth Hochschild cohomology will be defined as the n-1 cohomology of C bullet of A, which is, if you don't know what cohomology is, just a kernel of dn-1 modulo the image of the n minus 2, where the n is just a restriction of the differential to the degree n. How much time? Okay, then I'm still doing good. Probably can write the first word. Hmm. That's the Hochschild cohomology. And now, another proposition, and I will finish with this. Uh, um, that m and n be greater than or equal to -1. So integers, then the map. I also denote by bracket from h m plus 1 of A, tensor h n plus 1 A, comma A, to h m plus n plus 1 of A, which maps F tensor G. So by this underline, I denote cohomology classes associated to elements of the kernel of dm or dm plus 1. And I map this to the bracket of f and g, and then the corresponding cohomology class. This is well defined. Is well defined. And turns now I have the Hochschild cohomology of A shifted by 1. Turns this object into a graded Lie group. The map. This map has a name, this bracket. This is called the Gerstenhaber bracket. Okay, do I have time for a proof? It's only 2 minutes. Okay, what we have to do is first we have to make sure that this bracket of f and g lies in the kernel of dm plus n. This is easy. So okay, let's slowly have this kernel of dm g is in the kernel of dn, and then if I apply d to the bracket of f and g, yeah, this is df g, then -1 to the degree f f dg. Okay, but this is 0, and this is 0. This is equal to 0. So I do get m plus n plus 1 co-cycle if you want. And now if m F is a co-boundary. It means that F is an image of dm m minus 1. A. Then my management of space is not optimal. Okay, then what do I need to check? I need to check that bracket of f and g will be 0 in the cohomology. So what is it? So bracket of d, f, and g is again by the Leibniz rule the same as let's consider cohomology classes the same as d, f, g minus and probably some minus 1 to the degree f. F and then d of g. So this becomes 0 in cohomology because it's the image of some element. Yeah, it's an image of d. And then here this dg is also 0. So in total this is 0. And yeah, we have a well-defined map. And I think this is a good point to stop.
Are there some questions?
Just curious to know if is there any dual notion of Hochschild homology, maybe?
Yeah, there is. So alternatively, you could define the Hochschild homology as a derived functor. And there are two versions of derived functors. There's two basic versions. There's X and Tor. So the Hochschild cohomology would be X. So you take a projective resolution of the regular AA bimodule and then apply homomorphisms to A. This gives you the Hochschild cohomology. And for the homology, you would take the resolution and just tensor it with A. Yeah. And this gives you a chain complex, and the homology of this complex is the Hochschild homology.
Okay, thank you.
Just about the proof you just did. So two questions. In the first line, what are we, or second line, what are we showing? We're showing that D of the bracket is 0. D of bracket of G is 0.
Exactly. So what we want to do is we want to check that this is well defined. So if I take element that is 0 here, this should give me 0 here.
Right. Yeah.
Yeah.
Okay. And then in the very last equation, why is this the first term D of bracket FG? Yeah, why is that 0?
So the cohomology is defined. So I factor out the image of the D. And so this element is of the form D of something, so it's in the image of D.
So
that's why it's 0 in the cohomology.
Yeah. Okay, thank you.
So, I mean, the notation is suggestive that it's in general some kind of bivariant theory. You can have like HHAB instead of AA. Is that?
Yeah, if you know derived functors, you could replace the second entry by an arbitrary. I don't know if I'm not quite sure if A module or A bimodule. Yeah.
Okay, right. And also, so for example, in degree 0, what does this tell you about?
So it was one remark I originally wanted to make. So in degree 0, you get back the center of G, the center of A, and in degree 1 you get the derivations, but not quite the derivations, but modulo so-called inner derivations. And in the second Hochschild cohomology, tells you the infinitesimal deformations of your algebra E. Yeah. So this is quite useful invariant of your algebra.
Maybe also a question. So you started with a vector space, and this gave you a graded Lie algebra. Then with an algebra, you get a complex, so a cochain complex, right? And so what if you ask more like, what if your input is a bi algebra or a Hopf algebra? Can you get even more structure?
Okay, probably if you have a bi-algebra, so the thing is you only consider maths with multiple inputs. But if you have multiple outputs, you need to start with a different kind of complex, probably.
True, but let's say for a Hopf algebra, you have the antipode. This would have one input, one output.
I don't know if it would tell you much because it also needs to see the coproduct. You don't see the coproduct in the Hochschild space. Probably where your question is leading is the notion of properads, which I don't know much about.
But this would mean that you can have like even multiple outputs, and then the coproduct would be more interesting, right?
Yeah.
Okay. Are there more questions?
Yes. Can you hear me?
Maybe some questions from online audience. If this is not the case, then let's thank the speaker again.